Okay, I think we're good. All right, so if you have any questions to start off with, yeah, I'm going to record this and post it somewhere. If you have any questions to start off with, what I did was I posted the solutions to the review session problems that were sent out. So I'm just not planning on doing those at all. If you have questions on those problems, then go ahead and ask. But I sent out I posted the solutions, and then I sent out a new set of problems that we'll work on either Wednesday or Monday or maybe both. Okay? All right, so we'll get started. We'll start with a quick review of energy and Newton's laws, and then we'll talk about rolling and how we use energy to solve problems with things that are rolling. So let's see, did we do, I think we did this one last week. I hate to do the same problem again. Let's see, how can we mix it up a little bit? No, let's throw a spring in there. How about that? That changes it a little bit. Okay, so what we have here, two masses. I think we did this problem. Question about pre-lecture assignments. I'm not hearing the audio very well, but I do see a question of pre-lectures. Sure, let's turn them in when we get back next time. I'll collect them. Yeah, if you don't think the pre-lectures are helping you, as I've said in the past, just do something else. Show me you've done something to look at that material. And actually, the whole point of those is to make sure you've looked at the material ahead of before lecture. So I guess I will not collect those. How does that sound? And then I will just collect the next pre-lecture that's due starting tomorrow and Wednesday. Okay? All right. Let me work through this one. We're going to start off with looking for the speed. So given M1 and M2, we would have to know, what just happened? We would have to know the mass of the pulley. The radius of the pulley. And that the pulley is a solid disk. What else do we need to know? The spring constant, H, and starts from rest at the equilibrium position of the spring. And we want to find the final velocity just before M2, oops, hits the ground. It would help if you could mute your microphone unless you're ready to ask a question, and then unmute it and ask your question. Thank you. All right. I think we're good here. Okay, so this is our favorite problem, right? Now our pulley has mass, and I've thrown a spring in there. I think I did the problem the other day in class without the spring. Maybe not. Okay, so because, again, think about what you're asking for, what you're being asked for in the problem. We're looking for a final velocity. So this is probably an energy problem, right? What we're going to do next, we're going to do the same problem again, but we're going to look for the acceleration. And if you're looking for acceleration or tension in the string or something like that, that's forces and masses and accelerations. Think F equals ma, Newton's law. If you're looking for a final velocity, then energy is probably a more straightforward approach. So we will use energy. All right, so I'm just going to go ahead and make up an energy bar chart here real quickly. Remember, we'd like to say E initial is equal to E final, but some stuff gets in the way, right? Friction might get in the way. Do I have friction? Oh, I forgot something here. I have to add in mu sub k here, friction. Okay, now I think we're good. And external forces might act on our system. Now we're good. Now we have an equation. The initial mechanical energy plus the work done by friction plus the work done by external forces is equal to the final mechanical energy. So what is mechanical energy? It's kinetic energy. And for every mass in our system, we could have kinetic energy, right? And we have three masses now in our system, M1, M2, and the pulley. So there's possibly a kinetic energy 1, kinetic energy 2, and I'll just call it K rotational for the pulley, but whatever you want to call it. Kinetic energy for the pulley. All of those masses might go up and down, right? So we could have a U gravitational for mass 1, a U gravitational for mass 2. Our pulley is attached to the Earth, so I'm not going to include a gravitational term for that. If the pulley was going up and down, then I guess I would need a gravitational energy for that too. And if we have springs in our system, we need a spring potential energy for every spring in our system. We do have one spring, so I'll have one term there. I'm going to move this over a little bit. It's going to run out of room otherwise. And then we have friction. We don't have any external forces. If we define our system properly, we shouldn't have any external forces because we don't have any hands reaching into our system or just one end of a string sticking into our system. If you have those situations, then you have external forces. And then at the end, we're going to have all this same stuff again. I'm just going to copy it. All the same stuff again. But now it's the final energies. And so our equal sign goes right there. And this is going to be our bar chart. Right? So let's ask ourselves, is anything moving at the beginning of the problem? No. They start from rest. So I'm going to go ahead and put 0 kinetic energy for both masses and the pulley. Nothing's moving at the beginning. Is anything moving at the end? Yes, everything is moving. So we're going to have kinetic energy, and kinetic energy is always positive. Both masses and the pulley all have kinetic energy. Does mass 1 move up or down during the system? During the time this problem takes place? Yes, mass 1 moves up. So I'm going to call the lowest point in the problem 0, and then at some later time, it has a final y value that's more than the initial y value. It's gone up, right? It's going to be over here at the end. It's moved by a distance h up the incline, and box 2 goes down by a distance h. So I'm going to call its initial gravitational energy 0, and then it goes up. So what has to have more gravitational energy if it goes up? So that would be some positive amount. Mass 2 goes down. So it starts off, I'm going to say it starts off with some gravitational energy, and it ends up with 0. Starts off with some positive gravitational energy, ends up with 0. We have a spring in our system. At the beginning of the problem, the spring is at its equilibrium position, so it has no energy stored in it. So I'll have a 0 for the spring potential energy at the beginning. But at the end, it's stretched. Doesn't matter stretched or compressed. Either way, it has energy stored in it, and that energy is always positive for spring potential energy. Now let's go back and take a look at friction. We do have friction in the problem. We just have friction on mass 1. And so that's only one friction term. The work done by friction is negative. So I'll have some amount of work done by friction there. And I have no external forces reaching into my system. I'm including the spring in my system. I'm including the earth in my system. So I've got no external forces. And so there's my bar chart. So this will help me set up my equation. So the first thing I've got, as I look over, I've got a bunch of zeros, right? 0 kinetic energy, 0 gravitational energy for mass 1. Now I have some energy, gravitational potential energy for mass 2. So that's going to be m2 times g times its height, and its height is just h. It starts off h above the ground, and it ends up on the ground, or a split second before it hits the ground, so it's almost there. So that's a height h. And now I'm just going to keep moving along here. I've got the work done by friction, so don't forget your minus sign. The friction force times the distance that it moves. And how far does it move up the incline? H, right? Distance is h. So the friction force times the distance times the cosine of 180. That's where the minus sign comes from. And that's everything on the left side of my equation. On the right side of my equation, I have a 1/2 m1 d final squared. I have a 1/2 m2 d final squared. And I have a rotational kinetic energy, 1/2 I omega final squared. I have a gravitational energy for mass 1, m1 g, and its height. What's its height at the end? It's going to be this distance here is what we're looking for. I'll call it h prime. And h prime is just equal to h times the sine of theta. And where are we? Oh, we've got one more term here. We've got spring potential energy, always positive, 1/2 k x squared. And what is the distance the spring moves? H, right? M1 moves the distance h up the incline, and that's how much the spring gets stretched. Okay, so there's just a few things I have to fill in here. M2GH, that's all good. Those are all given values. The friction force is mu times the normal force, and this is M1, and it's on an incline. And H is given, and then we have a 1/2 M1 squared, 1/2 M2 d final squared, a 1/2 I. What is I for a pulley, solid pulley? 1/2 M pulley R squared, that's I. For a solid disk. Omega is V over R. And then we have our last two terms, M1 G H sine theta and a 1/2 K H squared. Okay, so now I'm done. Now I have the only unknown in this equation is V final. Now I can solve for V final. We okay with that? Up until this last line, it was the same as if we had a massless pulley, right? What's different now is we have an I here. Rotational inertia we have to plug in for. And in this case, we could just look that up right in our table on our formula sheet. A solid disk rotating 1/2 mr squared. And then we have to substitute in for omega in terms of V. And we know at the rim of the pulley, V, the linear velocity, is equal to R times omega. And at the rim of the pulley, that's the speed that the string is moving. That's the speed that M1 and M2 are moving. So these V's now are all the same velocity. Okay. I went kind of quickly through that because we've seen these types of problems a number of times, right? There's just one little twist here at the end with having a rotational energy component. Okay, so now we'll spend a little bit more time on this problem, but we're not going to solve for using energy. We're going to take the same problem again. I'm just going to cut and paste a little bit. Okay, so same problem. Given M1 and M2, M pulley, R pulley, pulley's a solid disk, we've got some friction, the spring constant, the distance it moves, starts from rest at the equilibrium position of the spring. We want to find T1, T2, and the acceleration. And where do we want to find it? How about the split second before M2 hits the ground? Okay. So the acceleration is not constant, right? There's a spring in our system. Spring in the system. So that means the acceleration is not constant, but we want to know what the acceleration is the instant when block 2 has moved down by a distance h, and block 1 has slid up the incline the distance h. And so we can do that. Would friction change the acceleration of block 1 at all? Yes. Yeah, without friction, then the system would have greater acceleration, right? Friction is going to slow block 1 down as it tries to accelerate up the incline. No, they're connected. They're all tied together. We'll assume that the, let's see, in this case, nothing can cause the tension, the rope to go slack. So if it's a release from rest and M2 is big enough to cause this whole thing to move downward, then they're all going to have the same acceleration. M1 and M2 will have the same acceleration, and that'll be linked to the angular acceleration of the pulley because they're attached with the string. Okay, so what I like to do, I know I'm looking for forces and acceleration. I'm thinking Newton's laws, right? Some of the forces equals ma, some of the torque equals I alpha. So I write a free body diagram. I draw a free body diagram for every mass in my system. I have M1, M2, and my pulley. M1 and M2 are not rotating. I'm just going to draw them as point objects. You could draw a box there if you want to. The pulley, I need to figure out torques. It's something that's rotating. So I have to draw the actual shape of the object and where the forces are being applied to it. This is a real free body diagram, not the one with just a point object like we've been doing so far. Okay, so let's draw our free body diagram for M1. We've got a tension pulling up. Call that T1. And we've got a spring that's going to be pulling down because the spring is in a stretched state, so it's going to be pulling back. We've got a normal force and a friction force. And then we've got gravity, and we're going to break up our gravity into M1, that should be an M1, G cosine theta, and then, oops, do it the wrong way, M1 G sine theta, down the incline. Okay, so that's everything acting on block 1. Block 2 is a little easier. There's just gravity and the tension in rope 2. And our pulley has a tension pulling on it on this side. That's T1. And a tension pulling on it on this side. That's T2. It also has its own mass, right? The mass of the pulley times G, and some kind of a support force. Those two, the mass, the weight of gravity, and the support force aren't really interesting to us because they don't produce any torque. They act at the center of mass, and so they don't produce any torque. We'll get to that in a minute. Okay, so remember here, T1 and T2 are no longer the same, right? Up until now, we've had massless pulleys, and so the tension on one side and the tension on the other side have been the same. But now with the pulley that has mass, the tension has to be different on either side of the pulley, or the pulley wouldn't accelerate. The pulley wouldn't rotate faster and faster and faster as the masses move faster and faster. So the tension has to be different on either side of that pulley because it has mass now. Okay, so what do? For every mass, we say sum of the forces is ma. Pick a direction as positive. I'll pick up the incline as positive. Sum of the forces is m2a. What direction is positive for m2? Down has to be positive, right? So once m1 goes in its positive direction. I've said that the positive direction for M1 is this way. Then M2 has to go in the positive direction. So the positive direction for M2 is going to be that way. And that way my accelerations are the same. If I don't do that, my accelerations are different, and that makes the problem a little trickier. And then we have the sum of the torque is I alpha. And what direction is positive? Well, when M1 goes up and M2 goes down, the pulley turns clockwise, right? So that has to be our positive direction. Another way of saying that is into the page. That's also denotes a clockwise torque. Okay, so let's start with M1. Sum of the forces in this direction. We only have one force in the positive direction, that's the tension, T1. In the negative direction, we've got our spring force, we've got our friction force, and we've got our weight in the x direction, sine theta. And that all has to be M1 times the acceleration. And for M2, we only have two forces. The weight of gravity minus T2 is M2 times the acceleration. And now for the torque, we have T2 is producing positive torque. It would cause the wheel to rotate in the clockwise direction. So I have a T, oops. There we go. Let me take one step back, write it this way. The torque from T2 plus the torque from T1 plus the torque from mg plus the torque from F support has to equal I alpha. Okay, now let's go fill these in. The torque caused by T2, that's going to be the force, T2, times its lever arm. And what's its lever arm? Just the radius of the pulley, right? The torque caused by T1 is in the negative direction, minus T1R. The torque caused by mg. You see mg goes right through the axis of rotation, the center of the pulley. So it has no lever arm. So it produces no torque. The support force passes right through the axis of rotation, of the axle of the pulley. It produces no torque. So that's why those are not as important there, because we know that they don't produce any torque. So what we end up with is T2R minus T1R is equal to I alpha. And we know what I is for a solid disk. This is a pulley with a solid disk, right? So let's put that in. 1/2 mass of the pulley R squared. And we know that alpha and A are related to one another. A is equal to R alpha. So alpha is A over R. And the left side of the equation has an R in it. So when we bring that over to the other side, all the R's cancel out. And we have an equation that just has the tensions and the acceleration. So that's one of our equations that we're going to need. We need 3 equations because we have three unknowns, right? So for every mass in your system, M1, M2, and the pulley, every mass in the system is going to give you an equation. So if we have three masses in our system, we can solve for three unknowns. In this case, it's two tensions and an acceleration. So there's our first equation. Our second equation is right here. That equation has only two unknowns in it, the acceleration and T2. And now we go back to our first equation and we plug in, we've got some things we have to plug in. What's the spring force? It's just Kx, which is H in this case. And what's the friction force? Mu times the normal force. And now we have an equation that only has two unknowns in it, tension and acceleration. And so now we have three equations, three unknowns. And we can solve for the tensions on either side of the pulley and the acceleration of the system. Okay? So what's new here is the whole rotational motion thing, incorporating some of the torque equals I alpha in with our sum of the forces equals MA. So, you know, the first two over here, same things that we've been doing. And so what's new is the part of, on the right, sum of the torque equals I alpha. Question, doesn't force of the spring change as the mass moves? Yes, it does. So you have to solve for this at a specific instant. So the acceleration is changing, right? As the mass moves, the force of the spring changes. And so the acceleration changes. So what I'm asking for here is the acceleration, the split second before M2 hits the ground. So basically, when M2 has moved by a distance h, that's the acceleration we're solving for. And at that instant, this is the spring force. At an instant before, it's going to be less than that. At an instant after, it's going to be, well, it's going to hit the ground. So I guess it would be very different then. But we can only solve for it at a specific instant. How would you solve for the unknown? So you've got three unknowns. So you solve for, what would I do? I would start with this equation here for M2. And I would solve for T2, right? T2 equals something with an acceleration and an M2 and a G. And then I would stick that into this. Every time I see a T2, I'd stick that in over here. And then I'd probably do the same thing over here. I'd use this equation for M1 and solve for T1. And then stick that in over here. And then I have one equation left with just the acceleration. And then I can plug those in and solve for the acceleration. Okay. Any other questions on this one? So what I want to do is talk about rolling, because a lot of times with problems that involve energy and rotational motion, we've got something rolling rolling down a hill, and we want to know how fast it's going when it gets to the bottom of the hill, something like that. So let's talk about rolling. So rolling is kind of complicated. What you've got is this situation. When something is rolling, let's see if I close enough. When something is rolling, it's really pivoting about that point right there, right? That's the axis of rotation. And it's moving kind of in this direction, right? So the velocity of that point right there is 0. It's not moving, right? It's the axis of rotation. The whole wheel is pivoting about that point that's in contact with the ground. The center of mass is moving with some velocity. The center of mass. And the top of the wheel is moving with a linear velocity that's how much? Twice as much as the velocity of the center of mass, right? Because it's 2 times the distance away. Okay, so at any instant in time, a point on the top of the wheel has a linear velocity that's twice as fast as the point at the center of the wheel, and the point in contact with the ground is not really moving linearly at all. It's just at rest at that instant. So that's rolling. So what we're going to do is say, is there some way that we can picture this that's a little simpler to understand? So what we're going to do is think about what's happening when something is just rotating and what happens when something is just moving, just translating. So if we have pure, let's start with the easy one, it's pure translation. So we have a circle. Pure translational motion. What does that mean? The whole circle is just moving to the right without rotating. So the center of mass is moving to the right. The point at the bottom of the wheel is moving to the right with the same velocity, right? The point at the top of the wheel is moving to the right with the same velocity. Every point on the wheel is moving to the right with the same velocity. There's no rotation involved, right? Just pure translation. The whole thing is just moving to the right without rotating. Now let's take a look at pure rotation. So if this thing is rotating without moving at all, the center of mass is not moving, right? It's just, I don't want to write the center of mass. The velocity of that point at the center is 0. The velocity of some point at the bottom of the wheel, if this thing is rotating clockwise, is to the left. I'm going to call that the center of mass, just because I've used that terminology for other places. So it's the same amount. And a point at the top of the wheel is moving to the right with that same speed. Okay? So if something is spinning and it's not moving at all, the center of the object is fixed. It's not moving, but the top would be moving, have some velocity to the right if it's rotating clockwise, and the point at the bottom would have some velocity to the left, the same equal velocity to the left at that instant, right? Now let's combine these. Let's add these together. And what do we get? We get the center of mass. We get the center of mass plus 0. So we've got the center of mass moving at the center of mass. The point at the top is moving how fast? To the center of mass. We're adding those two together, and we get 2v center of mass. And the points at the bottom, we're going to add those together. We're going to add those two together. What are we going to get? 0. So what does this look like over here? Let's back up. It looks like something that's rolling. We took pure translational motion and pure rotational motion. So those are two things that are relatively easy to deal with. Something that's moving without rotating and something that's rotating without moving. Those are two relatively easy things to deal with. And we say if we combine them, we get something that's kind of difficult to deal with. We get something that's rolling. And so that's what we're going to do. Whenever we have a problem like this, we're going to say pure translational motion plus pure rotational motion is equal to rolling. Now we just have to figure out what the velocity of the center of mass is. Because there's some link here between these two motions. So let's take a look at an object that's rolling. Okay. So what we've got here, we've got a wheel that's going to roll to the right. And I'm just going to mark 2 points here. A is in contact with the ground, and B is some other point up here somewhere. Okay? So I've got this wheel. It's touching the ground at point A, and I'm going to roll it forward until point B is touching the ground. But before I do that, I'm going to get out some paint, and I'm going to paint the edge of the wheel here between points A and B. Okay? I'm going to put a little paint on there. Now I'm going to put point A on the ground, and I'm going to roll this wheel forward until point B is touching the ground. So this is a later snapshot. What's touching the ground here? Point B. And where is point A? It's up here. Okay. And what's green? This whole surface now is green, right? So what distance is this? This is the arc length, S. And what distance is this between A and B? It's the same distance, right? You can see from the green paint that that's the same distance. So the center of mass of our wheel moved by the arc length that the wheel has rolled through. Does that sort of make sense? Why am I doing this? I'm trying to link the velocity of the center of mass to the rotational velocity omega of the wheel. There's a connection between those two. So at the rim, the velocity, linear velocity on the rim of that wheel is equal to r times omega, right? And we know that that is also equal to the velocity of the center of mass, because of what I just said, right? The distance s is the same distance that the center of mass moves. So the linear velocity at the rim is equal to the linear velocity of the center of mass. So that means that the center of mass is equal to r, I'm using a capital R omega. And this is true if something is rolling without slipping. Right? If it's rolling without slipping, we know there's this relationship between the angular velocity of the wheel, the rotational velocity, and the translational velocity of the wheel. If it slips as it rolls, then all bets are off. We don't know the relationship, right? Okay, so what does this all mean? Let's do a simple problem with the wheel rolling down a hill, and let's figure out how fast it's going when it gets to the bottom. Let's see, let's do a, how about a ball rolling down a hill? Let's make it a hollow ball, like a basketball. Right, something that's filled up with air on the inside, and it's a hollow spherical ball. And let's give given it rolls without slipping. Mass m, radius r, starts from rest, and starting height h. And we want to find the velocity of the center of mass at the bottom of the hill. So I'll draw you a little picture here. We've got a hill. We've got a straightaway. Well, I'll make the transition a little smoother than that. Something like that. And it starts here. And it's going to end up rolling down the hill. And we want to know how fast is it moving. How fast is the center of mass moving when it gets to the bottom? Okay? Yes, yeah, we're going to say that the rotational velocity, well, what we're trying to do is link omega, rotational velocity of omega, to V center of mass. And so we're going to say that V rim and V center of mass are the same. You'll see in a minute when we get there. So if we do an energy energy for this, then we can solve this, right? So first thing we're going to do is say that this thing is not moving initially, so but it does have some gravitational energy, right? All of its energy is in the form of gravitational energy at the beginning. And at the end, it's moving. It's rolling. But what we've said up here, the whole point of this little exercise here, is that instead of dealing with something that's rolling, which is kind of complicated, we're going to say it's just as if it magically becomes two objects, one that is just moving without rolling, and one that's rotating without moving. And so at the end, it's going to have both a K translational plus a K rotational. So now the big question is, what about friction? We've got no external forces, right? I'm just going to call that 0. We're including the Earth in our system, so we've got no external forces acting on this. What about friction? Is there friction between this object and the incline? Yes, there is, because if there wasn't friction, we wouldn't be rolling, right? It would just slide down the incline. So there is friction there. But what kind of friction is it? It's static friction, right? Static friction, because our wheel, or whatever, the ball, the basketball, is rolling without slipping, right? So this is static friction between the ball and the ground. And so it does no work. So the work done by friction is 0. It's only static friction. There's no kinetic friction here. So let's talk for a minute about something called rolling friction. I'll have a little aside here, and then we'll come back to this problem. So what happens when a real-world object rotates, like the tires on your car? When they rotate, they deform slightly. So you have an object here. This is always hard for me to draw. Well, everything is hard for me to draw, but this is particularly hard. Here, let me try this. So as this object rotates, like the tires on your car, they bunch up a little bit right here. Right? A real world object that can deform a little bit, like rubber tires. Okay? So what that means is the rubber on your tires is getting pushed together a little bit, deforms, and then as soon as your car goes over that spot, it goes back to normal, right? And the next little section of tire in your car bunches up. And so the tire, the rubber, is getting flexed a little bit, and there's friction in there, and it heats up. Another way of thinking of it is that this is like a little hill that your car has to go over. So your car is always sort of trying to climb this little hill that it's creating in front of the tire itself. The tire itself bunching up creates this little hill that the tire is always going over. And this causes you to lose mechanical energy. So in other words, if I had this tire and I started it rolling on a perfectly horizontal surface, a real world rubber tire that can deform a little bit, and I started it rolling on a perfectly horizontal surface, it would eventually come to rest. It would lose its mechanical energy to heating up the tire, the deformation in the tire. That's called rolling friction. And that's a real problem with things like car tires. That's why you have to keep your car tires inflated to the proper pressure. It keeps them nice and stiff. If you let them go soft, then this deformation is more exaggerated, and you get worse gas mileage, right? You want to keep your tires inflated to the proper pressure, but don't overinflate them. That's not good either. Just go with the proper pressure that's recommended by the manufacturer. Okay, so this is a tricky thing to deal with. This is there in real world objects that can deform, and so what we're going to say for our cases here, to make it a little easier, we're going to say that our objects are perfectly rigid. They do not deform at all when they roll, and so we don't have rolling friction, and that means the problem's a little bit easier. So if our object cannot deform at all, if it's perfectly rigid, and we started it rolling on a horizontal surface, it would just keep rolling forever on that horizontal surface, right? So that's what we're going to pretend here. No rolling friction in our problem. Okay, let's get back to this problem. So we've got a gravitational energy. So h is this height just above the ground. Okay, and so that's just mgh. That's our initial energy. At the end, we have as if the object was just moving, 1/2 the mass of the object times v center of mass squared, and as if it's just rotating, 1/2 I omega squared. And the I we're using is the I about the center of mass. Right? As if it was just rotating about its center of mass. So for a hollow basketball, I is 2/3 mr squared. And we know omega, we can substitute in v center of mass over r. So now our equation becomes mgh is 1/2 mv squared plus 1/2 times 2/3 mr squared times, I guess I shouldn't go back and forth between lowercase r's and capital R there. Times omega squared, which is going to be v center of mass over r squared. And so what do I end up with? I end up with the 1/2 mv center of mass squared plus a 1/3 mv squared. That's 5/6. And then I can solve for v center of mass. Okay, so I talked a little bit about rolling and the fact that rolling is pretty complicated. It's rotation about this axis right here, that's in the point that's in contact with the ground. That's kind of tricky to deal with that. But you know, what's not so tricky is pure translational motion and pure rotational motion. And when you can combine those, it's as if it's rolling. It's the same as if the object is rolling. And so that's what I did. And then this little example, I hope, kind of pulled it together for you. At the top, we had only gravitational energy, but when it got to the bottom, it was rolling, and we treated that as if it was really two objects, one that's just moving without rotating, and one that's rotating without moving. And when we do that, we get these two equations here, 1/2 mv squared plus 1/2 I omega squared. The I is about the center of mass, not the point that's in contact with the ground. And it just makes the problem much simpler if you view rolling as this combination of translational and rotational motion. Rolling friction, no, we're not going to deal with rolling friction at all, but I just wanted to explain what that was because it's a real world phenomenon. You hear about it a lot with tire pressure in cars and things like that. Maybe you were wondering why it's so important to keep your tires inflated to the right amount. Most objects do deform a little bit as they roll, and so you have rolling friction. But for our purposes, no, our objects will all be perfectly rigid. You want to find the acceleration of the object. You could do that. So what you would do is you'd pick, you'd have to find some point on the hill here and draw a free body diagram, and you say sum of the torque equals I alpha and sum of the forces equals MA, and you could figure out the acceleration that way. Okay, so what I wanted to do, where are we? So we've basically gone through, did a quick review of an energy problem with a pulley that has mass. We did a Newton's law type problem where we had to use some of the torque equals I alpha as part of the problem. And then we talked about rolling, so now we can do energy problems where things are rolling, which does happen. Things like that. Oh, question, why don't they just make the tires solid so we don't have that problem? Well, I think your ride would be much bumpier. Your car would be much noisier. If you lived near a road with a lot of cars going by, it'd be very noisy. And yeah, I think having the rubber tires on cars solved a lot of problems. Noise, like I said, the smoothness of the ride, not to mention the fact that what happens when you try to stop suddenly and you have steel tires or steel wheels right on the road, you have a very low coefficient of friction. So your ability to start and stop and turn will probably be greatly reduced. So tires solve a lot of those problems also. It's also a lot easier on the road, probably. If everybody had metal wheels, it would probably chew up the roads a lot faster. Roads would always be being fixed, things like that. So I think it solves a lot of problems. Okay. Yeah, so the tires, question about why not just making them solid rubber, that would probably work too. They'd be really expensive and heavy. What they've done, so when you go to buy tires next time, you'll see that they have some that are called high mileage tires or low rolling friction tires or something like that. I think what they've done is they've added reinforcements to the sidewalls of the tire. So if you look at your tire from the side, or I guess I should say from the front or back. So your tire looks like this, right? And it's rotating. There's the axle of the car, right? And the tires are rotating. They've stiffened this section in here. They've added some stiffeners into the sidewalls of the tire so that they don't deform as much. I think that's how they get the high mileage tires, things like that. So you get those stiffeners in there, and the tires don't deform as much as you drive, and you get less rolling. Yeah, the Martian rover had solid tires, but the Martian rover had to deal with the void of space, right? It's you're launching that thing with in a vacuum, basically. Whereas our tires on Earth, we have atmospheric pressure pushing in, so we can fill them up with air. They're light. It's easy to deal with them. Yeah, I don't know. It works, I guess. If there was something better out there, hopefully somebody would have figured it out by now. But I like the way you guys are thinking. Okay. So I'm ready to start angular momentum. So what we've got is the similar situation to linear momentum, right? What happened with linear momentum, somebody noticed, Newton, I guess, that when you take Newton's law, sum of the forces equals ma. And what's the definition of A is dv dt, right? And then you say if the mass is constant, we can bring it inside the derivative. And that tells us that there's something special about this quantity. There's something special about that quantity. If the net force is 0, that's what this is on the other side. If the net force is 0, then that quantity cannot change in time. It's a constant in time. And so let's give it a special name. Let's call that momentum, because there's something special about it. When the net force is 0, we know that this is a special quantity. It can't change in time. It's conserved. And so we use momentum to solve a lot of problems where we couldn't use other things, or it would be much more difficult to use other things. Now we're going to do the same thing with our, to get torque. Sum of the forces is dp dt. Right, P is our momentum. I just I'm starting with this on my other side here. Right? And now, this might not be something you would normally do, but we're going to say R cross the net force and R cross dp dt. And R cross F is the torque. Net torque. And so there's something special about this quantity, R cross P. When the net torque is 0, that quantity is conserved. It does not change in time. So we give it a special value. We call it a special name, L, angular momentum. The angular momentum is R cross P, and that's for objects moving in a straight line. we already know we use I omega for rotating objects. Okay, so let's take a look at this situation. You're probably wondering how something moving in a straight line can have angular momentum. So let's take a look at this situation. We've got a kid at the park. So here's our merry-go-round with the handles on it. Maybe those big metal discs you see at the park, at the playground at the park, can rotate about its center point. And the kid is running along here. And so kid runs along, jumps onto the merry-go-round. This is our initial state. Okay, so initially the disc is just sitting there. It's not rotating at all. The kid's running toward the merry-go-round, jumps, lands on the edge, and the whole thing starts rotating. So would you agree that at the final case there's some angular momentum to the system? Right, we have something rotating, right? L is equal to I omega. If we have some object with some rotational inertia, I, and it's rotating with some speed omega, it has angular momentum, right? It's not zero. So that means at the beginning, if you believe that that this system with no net torque acting on it, has to conserve angular momentum, then there must be angular momentum initially. Right, so L initial must be non-zero. So the disk is not moving. So the kid running in a straight line has to have angular momentum. And the reason the kid running in a straight line has angular momentum is because when the kid collides with the merry-go-round, it starts rotating. The kid might be running in such a way that the merry-go-round does not start rotating, and then the kid would not have angular momentum. So let's look at this example. The merry-go-round is sitting there at rest. The kid is running, jumps, lands on the merry-go-round. Does the merry-go-round start rotating? No. Because the line of the kid's momentum went right through the axis of rotation. When the kid crashed into the merry-go-round, it didn't cause the merry-go-round to start rotating because it was in line with the axis of rotation of the merry-go-round. So in this case, there's no angular momentum afterwards, and there's no angular momentum initially. But in this case up here, because the line of the kid's momentum does not pass through the axis of rotation, because it does not pass through the axis of rotation, that means when the kid collides with it, they can get this thing rotating. And so if they can get it rotating, then they have to have angular momentum beforehand. So we'll think about that for a minute. Okay, so here we have an object moving in a straight line. Mass m, velocity v, and we've got a point over here. This is going to be our axis of rotation. So you see, when you're defining angular momentum, you have to know what the axis of rotation is. It's different about different axes of rotation, kind of like rotational inertia, different. Same object, change the axis of rotation, and I changes, right? And the same thing is true with angular momentum. So if we're defining some point over here as being the axis of rotation, and our particle is moving with velocity v in this direction, then what we want to do is figure out what the angular momentum is. So this is r. R is the vector from our axis of rotation to our mass, to the location of where it's located. And let's call this angle right here phi. And we just saw a formula that said L is equal to R cross P, right? So what does that mean? That means it's the magnitude of R times the magnitude of the momentum times the sine of the angle when you put their tails together. I'll call that theta for now because I haven't drawn these two vectors with their tails together. So if I put the tails together, if I have an R vector that does this, what is it doing? Is that about right? Let's try one more time. R, if I move R up like this, close enough. I'm just moving the R vector up so that the tails of these two vectors are together, right? When I put the tails together, that defines what that angle has to be. That angle right there is theta. So let's see what I've got here. I've got R. What is P? P is mv. And theta is the sine of 180 minus phi. And the sine of 180 minus phi is just phi. And this is just the perpendicular distance. I'm going to call it d perpendicular. The perpendicular distance, I'll use green. the perpendicular distance from the line of the momentum, the line of the velocity, to the axis of rotation. You see that? R sine phi is just that distance there. That's the opposite side. So I like to do it this way. Instead of saying R cross P and trying to figure out what it is, I just go right to this equation right here. L is the momentum, mv, times the perpendicular distance between the line of the momentum and the axis of rotation. So let me do this at a split second later, right? So at time 0, we've got our mass and our velocity and our axis of rotation. And at some later time, it's over here. And at some later time, it's over here. Right, the object is moving to the right. What's the angular momentum at t0? Well, we just did it, right? It's the momentum of the object, mv, times the perpendicular distance. We extend this line. We find the perpendicular distance here, and we put that in there. I'll just call it d perpendicular. What's the angular momentum? Oh, we need a direction. What's the direction of the angular momentum? The best way to picture that is if we had some kind of a big object here attached to that axis of rotation right there, and this ball, or whatever that is, this object crashed into it, what direction would it rotate? It would rotate clockwise. So when this would cause clockwise rotation. So the angular momentum is in the clockwise direction or into the page. Right, use your right hand rule. So what is it at T1? You're going to take the momentum, mv, extend the line of force, sorry, the line of velocity, the line of the momentum, and find the perpendicular distance to the axis of rotation. It's the same thing here. What about time t2? You extend the line of the momentum, you find the perpendicular distance. It's the exact same in this case, right? And what direction? Into the page. Into the page, exactly the same. Think about it this way. If you had some funny shaped object here attached to that axis of rotation, and the ball struck it here, what direction would it cause it to rotate? Clockwise. And the clockwise direction is into the page. Use your right hand rule. Your thumb points along the axis of rotation, and your fingers move around in the direction of rotation, and your thumb points into the page. So they're all the same. Okay, let's do a problem with angular momentum. So we'll have some solid object on a pivot here. And it's just hanging there. And we'll have a little wad of clay comes along with some initial velocity. And we'll call this, what should we call this, a board hanging from a hinge. Some length, L. I'll use a lowercase l for the length of the board because capital L is for angular momentum. So I'll use a lowercase l for the length of the board. The mass of the board, it's just hanging there. And what happens, the clay collides with the board and it sticks to it. And this whole thing starts swinging with some omega. I'll call it omega 2. And then at some later time, it comes to rest momentarily, and then it swings back down. So time 1 is just before the collision. We make a timeline here. This is a collision type problem. This is just after. And this is later. Okay, so let's think about this for a second. We've got, this is a problem where we're looking for, what do we want to find here? How about find theta final given the other information? Here, given the length of the board, the mass of the board, the mass of the clay, the velocity of the clay, and let's have the radius of the clay be much, much smaller than the length of the board. So we can treat it like just a point object. And we want to find theta. And the object comes to rest momentarily. Okay, so let's think about this for a minute. Going from the beginning of this problem to the end of the problem using energy. Can we do that? No, because we know for sure when these two objects stick together that it's a inelastic collision. So energy, mechanical energy, is going to be lost to other forms that we can't account for. And so we can't go from the beginning to the end using energy conservation. Can we go from the beginning to the end using linear momentum? No. And the reason is that there's gravity gets in the way. We have this thing that's rotating has mass and dimension to it. So when we just had a simple pendulum, right, when we just had a light string with the mass on the end and all the mass was at the bottom, right, this was basically a massless. Then we treated this like two particles colliding, and we used linear momentum. Right, we could use linear momentum there. But now we don't have that. Now we have a rod or a board hanging here, and it has mass to it. And when it rotates, it's not the same as a linear momentum collision between two masses. So we really can't do that anymore. It was sort of a simple approximation we were making before because we didn't really have the tools to deal with those problems. But now we do have the tools to deal with it. And what we're going to say is that the sum of the torque is zero. So sum of the forces equals zero is what we need for linear momentum. And sum of the torque equal to zero is what we need for angular momentum. And so I guess we could have said maybe for some brief instant there that the sum of the forces were zero for that instant. But the problem is that we have an object colliding with an object that's a small point object colliding with an object that has mass distributed over its whole length, and it just doesn't work. If it was a simple pendulum with a massless string with all the mass at the end, we can use linear momentum, but we're not going to be able to do that here for this case because the rod has mass to it. So we've ruled out energy, we've kind of ruled out linear momentum, but angular momentum we're going to say is okay, that the axle here is low friction, and for the brief time that the instant that this collision is taking place, that there are no external torques on this, that gravity isn't acting on it yet, because obviously gravity is going to provide some external torque here and slow the thing down as it rises up. But for that instant, split second before the collision, the split second after the collision, we can say the net torque is zero. We're going to use angular momentum. To go from time 1 to time 2, right? And then once we get through the collision, then we're going to use energy. To go from time 2 to time 3. Okay, so the angular momentum at time 1 and at time 2 are going to be the same. Let's pick a direction. I'm going to pick my positive direction to be counterclockwise, or I should say out of the page, either way. Those are the same thing. So the angular momentum of the clay plus the angular momentum of the board initially has to equal the angular momentum of the clay plus the board at the end. They've stuck together, right? They are one. And so what is the clay? The clay at time 1 here is just an object moving in a straight line. So what's the angular momentum for an object moving in a straight line? It's m times v times the perpendicular distance between it and the axis of rotation. In that case, it's just L, right? You extend the line of the momentum, and you find that perpendicular distance, and it's equal to the length of the board in this case. Yeah, the clay is going to attach to the board, so you'll see how we treat that in a second. But yeah, we'll have to treat that like 2 different masses, basically, 2 different objects. Okay, so we are using angular momentum. When you're using angular momentum, always use angular momentum. Don't use linear momentum for one thing. Just because this is an object moving in a straight line, don't put linear momentum there and angular momentum here or something like that. Don't do that. If you're using linear momentum, use linear momentum. If you're using angular momentum, use angular momentum. But don't mix and match. Never, never mix and match in the same equation. They are independent equations. They both might be true. You might be able to use linear momentum and angular momentum in the same problem, but you don't mix and match in the same equation. They're 2 independent things. Okay, our board is, what did I do? I erased part of my plus sign there. The angular momentum of the board is 0, right? It's just hanging there, it's not moving. And at the end, excuse me, we have something rotating, right? And what's the angular momentum of something rotating? I omega. And this is, I'm going to call it I total, because it's the board plus the, it's whatever's rotating, right? Okay, so on the left side of the equation, we have the angular momentum for an object moving in a straight line. On the right side of the equation, we have angular momentum for a rotating object. Now, what's rotating? The left side of the equation I'm not going to mess with right now. Let's leave it the way it is. What's I total? We have I for the clay plus I for the board times omega. So we're going to treat the clay as a point object, right? So that's just mr squared, right? And what is r in this case is the distance from the mass to the axis of rotation. That's just L. And for a board rotating about its endpoint, we look that up, 1/3 the mass of the board, the length squared, times the length squared, 1/3 ml squared. That's not squared, omega 2. And we know everything. We know everything here except for omega 2. Now we can solve for omega. So now we know the omega, how fast it's moving, the split second after the collision. And then we can go from 2 to 3 using energy. Interesting question. When we walk, we have both angular momentum and linear momentum. So you kind of have to pick what axis of rotation you're talking about. If you're, you certainly have linear momentum if your center of mass is moving in some direction, you have linear momentum. Oftentimes with angular momentum, you think about, well, would it cause rotation? So if you just think about your body moving, here we have a top view of a person walking. We're looking down, you know, from a helicopter, top view of a person walking. And if there's an object here that could rotate, let's see. Let's say there's a door here with a hinge. Well, this person walking along, if they collide with that hinge right there, are they going to cause the door to rotate? No. So the person, even though they're walking and they have linear momentum, they don't have any angular momentum with respect to this axis of rotation. If we move the door over, or the person over, whatever the case may be, now if the person collides with the door, they cause it to rotate. So the person has angular momentum about this new axis of rotation. They did not have angular momentum about the old axis of rotation. So you kind of have to define what your axis of rotation is and think that way when you're thinking angular momentum. But when your legs are rotating, they have angular momentum about your hips. Certainly, that would be true. That would be treated like a rigid object or a solid object that's rotating. Okay, so let me finish this real quickly. So at time 2, we have all k rotational. And at time 3, we have all gravitational potential. So 1/2 I omega squared, that's kinetic energy. That has to equal the mass of the clay times g times the height that it rises up to, plus the mass of the board times g times the height that it rises up to. And if we have an object like a board here, I guess I shouldn't have drawn 2 of them. Dash, one of them would have a solid line. So this thing rotates up like this, and the center of mass of the board starts here and ends up here. So it's gone up by that height, right? HB. And if you work through it carefully, if this is theta up here, then you end up with the height of the board is L over 2 minus L over 2 cos theta. And the clay goes from here to here. So its height is bigger. It's twice as much. It's L minus L cosine theta. You want me to work through that a little more carefully? Let me just do one. I'll just do the clay. So the clay is going from there to there, right? And so this distance is L. This distance, I'll use blue, is L cos theta, because this is L over here, right? And so this all-important height here is L minus L-co state. And it's for the board, that's for the clay. For the board, you just, all the L's become L over 2's because all we care about is where the center of mass of the board starts and ends. Okay, so let's go back real quickly. Here we had a problem. It was a collision, but it was a solid object rotating. And so instead of using linear momentum, we used angular momentum to get through that. L initial equals L final. Even though part of the problem had a small object moving in a straight line and part of the problem had something rotating, we still use angular momentum for the whole problem, beginning to end using angular momentum. And then once we did that, we solved for the final omega. But again, mv times d perpendicular, that's the the angular momentum for an object moving in a straight line. And then I omega angular momentum for an object that's rotating. So just use the right angular momentum whether you have it moving in a straight line or rotating. And because these two objects stuck together, where does that come into play? It comes into play with the rotational inertia. So we have to combine the two rotational inertias of the objects, and then that fixes that problem. It shows us what the how we account for the two sticking together. It's just the rotational inertia changes. But we still treat it as one non-uniform object rotating. So how about we do I just want you to see that you can combine, if you have a kind of a complicated object, just like if you throw a bunch of different masses in the back of your wagon, what's the total mass of the wagon? You just add up everything that's in there, right? Well, what's the total rotational inertia of some complicated object that's rotating? Well, you break it down into simple objects and you add up all the rotational inertia to get the whole thing. So find I. For the pendulum of the grandfather clock. So it looks something like this. Here's our axis of rotation. And we've got a rod, a thin uniform rod. And then we've got a disc. Solid uniform disc. And we'll let this radius be R. And we'll let this be 2R. So the rod is going to have a length 2r, and mass m, and the disk is going to have a radius r and a mass, let's go with 2m. Okay, so think about how you would find the rotational inertia of this object. You would add up the rotational inertias of the shapes that make it up, right? So we've got I for the rod plus I for the disk, and that's how we would get it. So for the rod, that's just a rod rotating about its endpoint. That's 1/3 1/3 the mass of the rod times the length of the rod squared. The mass of the rod is just m. The length of the rod is 2r. And so what do we get? 4/3 mr squared. Now for the disk, we have to use parallel axis theorem. Because you look up on your formula sheet the disks rotating, and they don't have this disk rotating about an axis way off to the side. They have it rotating about an axis right through the center of the disk. But this axis is parallel to the one that goes through the center of the disk. So we're going to use I center of mass, which is 1/2 the mass of the disk times r squared plus the mass of the disk times d squared. And what is d in this case? It's this distance right here. The distance between the two axes of rotation. So in this case, it's 3r. So what do we get here? We've got the mass of the disk is 2m. And what do I get? 19. And then I add them up. 4/3 plus 19 mr squared. Okay, so rotational inertias, we can combine them. You have a crazy shaped object, break it up into shapes that you know and can kind of figure out, add them up to get the total rotational inertia. If you have to use parallel axis theorem or something like that, go ahead and do it. And then with energy problems, oftentimes we have objects that are rolling, and so we'll take that into account. So a couple of things there. One, when an object is rolling, the friction that's causing it to roll without slipping, that does not do any work. That's static friction that does not do any work, so we don't have to worry about losing mechanical energy to static friction. And the friction that would cause it to lose work is not actually friction. We call it rolling friction, but it's a deformation that takes place in the material as it rolls. and we're not going to deal with that pretty much in our cases here. We've got situations where our objects will be very rigid and won't deform, and we won't worry about rolling friction. And then when something is rolling, what do? We say it's as if it magically splits into two objects, one that's just moving in a straight line without rotating, and one that's rotating without moving, and we add up those two energies, those two kinetic energies, and it gives us the same thing as it would if we tried to take into account the actual energy of an object that was rolling, because that's much more complicated. And then we introduced angular momentum. So angular momentum is this special quantity that when there's no net torque on a system, it's conserved. So let's go back and look at our merry-go-round example real quickly. Here, I do the merry-go-round. Oh, here it is. Kid running toward a merry-go-round. So if you think about this case, can you use linear momentum to get through this? In the beginning, is there linear momentum? Yes, the kid is running, right? The kid then jumps onto a merry-go-round and is spinning. So that's not going to be the same as the final momentum. Why not? Well, because the merry-go-round is attached to the earth right there, right? And when the kid jumped on the merry-go-round couldn't move. It's attached to the earth, and so we can't use linear momentum to get through this. But if this is a frictionless axle, then there's no net torque on the system. And the kid jumps and gets on the merry-go-round, and it's free to rotate. And so there's no torque. And because the sum of the torque is 0, L initial is equal to L final. Excuse me. I've been talking too long. Okay, so work on this a little bit. I'll show you a case where you can use both linear momentum and angular momentum to solve the problem next time. But we've covered a lot here, so take a look at this. Any questions before we end this? So again, I sent out, or I posted the review. I called it review from November 14th, even though it didn't really take place that day. That has the solutions to those problems from last time. If you have any questions on those, let me know. We can go over it, but we've got to kind of move on. So I've sent out another review, some more questions that we can do at the review next time around. And that's out there, and you can see that. I did record this. I will see where I can load it, and I'll let you know. So I'm going to stop the recording. Let's see. How about you?